Okay, homework 13.2 is a little different problem. This time the room is going to heat the air, sensible heating, just like before, but it's also going to humidify the room, which we're going to call latent heating. So the temperature of the air coming in will be heated and humidified. The air comes in at 42 degrees, so this will be called state 2. Relative humidity of 80%. We have a volumetric flow rate of the coming air is 450 cubic feet per minute. To get a mass flow rate, then we'll have to find the specific volume. And then it heats up to 80 degrees and a wet bulb temperature of 65. So let's start by finding those two states. State 2 is 42 degrees, 80% relative humidity. We'll go ahead and take the sketch we had there and adjust these lines. So 42 degrees, this would be 40, 41, 42. And the slope looks pretty good. We can just adjust it a little bit. So since these lines aren't parallel, as we slide this temperature line around, we have to readjust the slope of the temperature lines. And then we're looking for 80%, so there's 100%, 90%, 80%, and it's where those two lines intersect that has to go through the 80% line, and then that's labeled up here. So there's our state 2, and then state 3, we need the temperature, which was 80 degrees, and looks like I need to adjust the slope a little bit. So that's pretty good, going through my 80 degree line. And then I need another line, so let me copy this and paste that. And what I did is I put this image in the header so that it doesn't keep getting selected when I'm sliding these around. And I forget the percentage, but maybe it was 60%. Actually, I think it was a wet bulb that was specified. Let's go back and check the problem. So I have 42 degrees and 80, which I think I did right. 42 and 80. And then 80 and 60 something. So let's move our line to be parallel with the wet bulb lines. And we'll check that again. It's 80 and 65. So I've got my 80 degree line. Let's put the 65 line, which is right there. And I need to adjust this a little bit to get the slope right. So let's see if we can find where that 65 degree line goes. Looks like it's about right there. And we can just zoom in to make sure. Okay, so there's my 65 degree line, which looks like I'm a little bit above over here, and if I stay just a little bit above, then I've got the right slope. So it looks like the whole way that little dashed line is just, I'm just a little bit above that line, so I'm going to go right on top of it. So I've got the right slope there. And the slope of the wet bulb line is a little bit steeper than the enthalpy line, so you need to be careful when you're not real close to the saturation curve, as those two lines will deviate a little bit. So now I've got the intersection of those two right there, and I'm going to read my other properties from that point. Looks like I can read this line right here and one down from it if I want my humidity ratio for that. I'm not sure if it asks for that, but I'll come over here. It looks like it's going to be on this line right below this. So this is 0.09 or 0098 for the humidity ratio. And humidity ratio at state 3 is 0.0098. And looks like I've got a little room for error there, but that's how I'm reading it off the chart. Then let's go back to the humidity ratio at state 2. So now I can find state 2 on here. And so here is state 2, and I'm just going to come down a little bit further. I think that 60-degree line cuts through about right there. So looks like whatever this line is, I'm a little more than 2 down, or maybe from this line I'm 2.5 up. So almost right in the middle between those two lines. So come over here, and that would be 0.004, and this is 0.005, so I'm going to say 0.0045. Okay, then I need to read my enthalpy, and I've got this blue line that's still aligned with my enthalpy lines, so I can drag this one over, and this should lie right on top of these solid lines, which are my enthalpy lines. So put that right at my intersection, and then I can read that. Gotta scroll over a bit. I'm gonna zoom out just after I read it, just to make sure. But that looks like 24.2. This is 25, 24, and then plus 0.2, 24.2. And just zoom out a bit. It's a little too much. And actually that was state, thing I looked, that was state 3. So 24.2 for state 3. Now we can move it down to state 2. And looks like right on 15. You can enter both of those. So I'm going to say 15. Of course, if I zoomed in, maybe I would have found 14.92. And let's double check that. So I thought I had 24. Let's check that again. So this is saying 29.9 is the right answer. Let's put that back. It wasn't state 2. That was, so state 2 was at 80 degrees, and this intersection right there. It looks like they're right on top of each other, but those two lines should deviate, so I probably should have labeled. Let me insert text box, I guess is okay. I was looking for shapes, but here we go. So put a little dot there. Don't really want to make it real big because then I can't see, but okay, so that's one of my states. That's my second state. This intersection is just it's the humidity ratio of state 2, but this is state 3 here. And if I insert some text, let's put a little text box here. So this is state 3. And over here, state 2. And of course, be the intersection. I don't need to put a dot there if I want. Maybe I can just copy this. Paste it here. a little irritating using Word to do this, but it's a little easier probably to follow than me doing it by hand. Okay, so that intersection state 2, the other state 3. And now I can read this other enthalpy, which is very close to 30, but we could maybe say 29.9 something, 29.95. All right, and specific volume of the air at state 2, I can try and read that. And here I have 13 and 12.5. So this right here would be 12.6, 12.7. This is 12.8. I'm going to say that's about 30% of the way. So 12.73. So this 12.6, 12.7, and then the next digit would be a 3. So 12.73. Right, then the mass flow rate would be the volumetric flow rate, which is 450 cubic feet per minute, divided by my 12.73, then I'll have pounds per minute, and I want it in pounds per hour. So just like, well, I guess I didn't have it here. Just scroll down a little bit. So m dot equals 450 cubic feet per pound of air divided by, just put that in parentheses so I know it's not the units, divided by 12.73 cubic feet per pound. So 450 divided by 12.73. $35.35. That's going to be pounds, or pounds of air per, this is, sorry, cubic feet per minute. So that's going to be pounds per minute. And then times 60 minutes per 1 hour. So that times 60 will be pounds per hour. So 2121. All right, and just see how I'm doing here on my values. I think they're all within range. So I've got everything correct so far. And then QT, the total heat gain for the space. So my total heat gain, QT, is equal to m dot times the enthalpy change, which is H3 minus H2, and those are pounds per hour, so I've got 2121 pounds of air per hour times, find the enthalpies here. I'm going to use the ones I found, so 29.95 minus 15. That's BTU per pound of air. So do the math there. 2121 times, I don't have parentheses, so let me do it the other way. 29.95 minus 15 equals 14.95 times 2121 is 31,709. And then finally, the mass flow rate of the water. So the mass flow rate of the vapor coming into the system would be the mass flow rate of the air times the difference in humidity ratio, omega 3 minus omega 2. But that's true because omega 3 is the mass of the vapor leaving divided by the mass of the air. So when I multiply times the mass of the air, that's going to be the mass of the vapor leaving minus the mass entering, and the difference would have to be the mass that's added to the system. So how much moisture is being added to the space through breathing, through water evaporating, whatever means the water's getting into the space, maybe perspiration of people. So that's going to be 2121 pounds of air per hour times omega 3. Back here, humidity ratio was 0098 and 0045. So if I do those, I get 11.24. So this is pounds of vapor over pounds air. Gives me 11.45 pounds of vapor per hour. Just double check that I did that right. 2.4 rather. Okay. All right, so double check my answers, and they're a little bit off from the values that I found, but everything's within the range of values between the equation and the charts. There is a little bit of difference, so don't worry too much if yours are a little off. These were calculated from equations, and the others were calculated using the psychrometric chart. One of the differences is the equations I used assume constant specific heats and the chart doesn't, so there'll be slight differences there. I hope that helped.